Thank you. It's nice to be here. I'm sort of the new guy around, new to not just Canberra, but Australia and even Tasmania, where I've been living for 6 months now. Come to join UTAS from 15 years in the UK. Today I'm going to talk about ice sheet models in a sort of overview sense, focusing on goals, progress, and challenges ahead.
Try the arrows on the keyboard.
Okay, so we've got two ice sheets on Earth, great ice sheets, as we're all aware, but they're actually quite different. And we need to consider them both, actually, if we want to address issues around sea level rise. In Greenland, we've got an ice sheet that's sort of situated in an island setting with coastal mountains. It's got enough water locked up as ice to raise sea level potentially by up to 7 meters if it all were to be lost. In Antarctica, it's much colder, windier, and drier. There's a lot more ice, enough to raise sea level by 8 meters in total. We're not really concerned about that at this point in time, but even a small difference in a large number can be a large number. That's what we are trying to calculate. Global mean sea level rise was an average 2.3 millimeters per year over the last 50 years. But recently, if we make that estimate over the last 15 years, it's increased to 3.7 millimeters per year. And that increase in sea level rise is predominantly tied to ice sheet contributions. Greenland's contribution increased from 4% of the total in 2000 to 18% in 2020, and Antarctic contribution increased from 1.5% to 8% in 2020. And it also shows why we as a community, as a young community, because prior to 2000, we weren't actually doing large-scale ice modeling very much because we were concerned about individual glaciers. It's really only this trajectory of ice sheets that's made us come into the sort of limelight and the setting that we are here today with modeling, large-scale modeling. So the goals in our community is really to understand ice sheet behavior and be able to predict sea level rise over the coming decades and centuries from climate change. So if you look at the latest report from the Intergovernmental Panel on Climate Change, the likely increase in sea level rise in this century is somewhere between 0.5 meter to 1 meter. But the IPCC also candidly state that we can't really rule out sea level rise on the order of 2 meters. So what's going on? The problem is that we have high uncertainty in our predictions in our community, and we've got low confidence in some of the key evidence that's important to tie this model into reality. So on the upper spectrum, in what we call sort of high-end estimates of sea level rise, extreme scenarios, we've got some model outcomes that are indicating that we could conceivably, in high-end estimates, get somewhere between 5 to 50 meters of sea level rise over a couple hundred years. But these predictions come from models that are quite coarse in resolution, have quite crude parameterization of processes. This will come from previous use in the paleo modeling community. So we're not entirely sure that we can utilize those parameterizations. However, it's also a problem that when we have really complex models, we are missing some of these parameterizations altogether. Or the parameterization is not necessarily much better. So we have this reality in between what we're deeming to be likely and this high-end scenarios that we can't rule out. So why are we so far from achieving our goal in our community? We know that the Amazon Ocean delivers heat to the ice sheets, but the forcing and ice sheet interactions with both climate and the ocean is really complex. The basal conditions of the ice sheet that dictates the response is complicated, and we don't have very many observations from the bed of ice sheets. I mean, think of it as your wind stress curve was residing at the bottom of the ocean and you had to drill through ice to get to observe it. That's our reality really in glaciology. Both forcing and response evolve over time, and there are positive and negative feedbacks that work together. So nevertheless, ice sheet models have come a long way, and they have progressed a lot over the last 5 to 10 years. And we're also starting to understand this uncertainty better. If we look at Greenland in the latest ice sheet model intercomparison project, we can see that there is a consensus between the different models and the different climate models that we force our models with. So we can see that there is a separation between what we project with our models based on high and low end emission scenarios. So let's see that the lower end of emission scenarios is separated from the high end. And we can see that there's a range of different outcomes, but they're consistent at least. If we look at Antarctica only in the high-end scenario, you can see that there's really a problematic response here. There's indication that we should see rising sea levels from contributions in Antarctica, but there's also models that are indicating that we end up with a mass gain due to increased precipitation and some changes in the basal conditions when we start to alter the ice sheet. But there's a high uncertainty associated with these projections. But we are understanding these uncertainties a lot more. So this is an example from a very recent study, and this is in Chan-both course. This is this work here showing that ice sheet model disagreement is really 45 to 80% of the total uncertainty. So that's an indication that we need to do better with our models. We need to make our models more consistent. And the good news is that we can bring this uncertainty down through operation with a better choice of ice sheet. So that's in some ways a good news, but it's also a clear message to us as a community here that we really need to choose our models quite carefully. If we go to 2300, this uncertainty actually goes away a little bit. And here's some examples. This is Jen Zhao's work, my colleague in UTAS, who's running a whole ice sheet model for Antarctica with the Elmer Ice finite element package. And what Jen's work shows very nicely is we're actually not uncertain about climate change for Antarctica in this time scale. You can see that there is an increased flux to the ocean that increases significantly after 2100. We can also see that after 2200 in these simulations, there's a stabilization and the ice sheet starts to pump less ice out into the sea. There is a high uncertainty associated with this. Jen and I had a nice discussion just last week about this. And she can actually, by changing the configuration of how sliding takes place under the ice sheet, she can double these numbers with models. This is something we are working to improve. Now I'm going to get back to that with another example in a couple of slides from now. So the challenges ahead is really priorities that we need to focus on and develop and agree on and making these models better. So we are working towards better initialized states, higher resolution, finding out what's the appropriate sliding law at the base of the ice sheet. We want to include hydrology and hydrological systems, which comes with feedback onto the ice sheet and its flow. Incorporate sediment and soft sediment that lubricate the basal motion. We want to apply our climatic forcing correctly. So the next example I'm going to go to is Yvonne's work, and he's here today as well. Please go and see his poster. He's using the Elmer Ice finite element package specific to Wilkes Glacial Basin. And I'm just going to bring out one example of the work that he's doing at the moment. And one of these tests is to look at the difference in the response of this large race basin in East Antarctica using two widely applied sliding laws, one being the Bergman law, the other being the Coulomb, that introduces nonlinearity between conditions at the bed and the way the ice flow. We don't really know yet which of these two should be used. But there's a huge difference in the response of the ice sheet to the climatic force, which is the same in these two experiments, based on whether we use one or the other. So we really need to make some progress in this work, because this will dictate clearly the amount of sea level rise that will come from Antarctica over the next 100 to 200 years. Right. So finally, I just want to highlight observations, crucial for making ice flow models better. The top panel here is a standard configuration of an ice sheet model. The bottom is what happens when we introduce observations from the field. In this case, some very precise temperature measurements that we made in Greenland. On the left-hand side, I'm showing this fiber table. And it really shows how exactly the ice slides over bedrock highs and in deep troughs. So we're starting to understand what kind of sliding law we should be using in different types of settings. So this is a promising line of work. Is that bell for 2 minutes or 5 minutes? Okay, cool. Okay, yeah, that should be good. Okay, so we're in this workshop. We have a goal. We want to make these better predictions. How do you get there? Well, we are actually, this is just the people I've met in the last 6 months. So it's not a finite list of what our community is. It's the people I've gotten to know, which is great. We are actually a vibrant community, and we are ready for this task. We just need to sort of configure ourselves and come up with a structured workflow, in my opinion. So what might that workflow be? Now, my suggestion is that we consider the problem in these three types of work packages. One, of course, being we want to understand the whole ice sheet and how it contributes to sea level rise. But if we just do that alone, we won't have the observations, we won't have the accuracy of regional scale models. And I think all of these three needs to be conducted at the same point in time and in unison to really be brought together. Aspect of Hugh's work was clearly on the basin scale. Chen's work is on the whole ice sheet scale. The example of separating and understanding what sliding law we should actually use came from observation. So we need to bring this together. That's it. Thank you.